Yes, good evening to one and all. On 25th, we discussed about introduction to concurrent programming. In that class, I discussed about what is the need of concurrent programs and what is the need of cache memory to achieve better throughput. The next day, Dr. Kalyan discussed about memory consistency models and cache coherence protocols. After that, yesterday, Dr. Saurabh discussed about how to design a lock. Okay. Yes, he also discussed about Peterson lock and some other techniques. Today, I'm going to discuss about different synchronization mechanisms. Before going to discuss some different synchronization mechanisms, I would like to discuss about different types of implementation techniques. Okay. Yes. Yes. Before going to enter into that, first of all, I would like to discuss the need of synchronization. Yes, as Dr. Saurabh pointed out, okay, we need a synchronization when two or more threads contend for a shared memory location at the same time, and at least one of them updates memory location. Then we face a problem of data race. Okay, to overcome that, we need synchronization. How do we achieve synchronization? We are going to achieve synchronization with the help of synchronization primitives, locks, and barriers. Right. Yes. After that, to design any concurrent program, we should take care of two things. Okay. First one is safety property. When we look at the safety property, actually bad things never happen. Here, bad things means concurrent program never into the problem of data race. At the same time, we never face a deadlock, right? Suppose if you face a deadlock, program will be stalled. Suppose in that context, we have to use some other mechanisms to come out from that particular deadlock situation. The next one is liveness property. Liveness property is anyhow we are using multiple threads to achieve better performance. That means we are expecting that some good things will happen. Okay, with that hope only we are writing the concurrent programs. Otherwise, there is no need to take this much trouble, right? Next one is usually when we look at the types of concurrent implementations, types of concurrent implementations are divided into two types. They are non-blocking implementation and blocking-based implementation. Non-blocking implementation. Non-blocking implementation means suppose due to some reason, okay, one of the multiple threads is stalled. Okay, all other subsequent threads can proceed for can complete their operation without any stall. Then such type of implementation is called a non-blocking implementation. Okay, blocking-based implementations, right? Suppose when we consider a particular concurrent implementation, if due to some reason, okay, one of the concurrent threads stalled, okay, then all other subsequent threads are going to be stalled. That is called a blocking-based implementation. Next, actually, when we usually concurrent implementations can be classified into two types: non-blocking and blocking. Okay. Yes, in non-blocking, again, we can classify implementations two types. They are lock-free and wait-free. Yes, lock-free guarantees that, okay, yes, some method is going to be terminated after finite number of steps. Okay. A wait-free guarantees that, okay, every method in that particular implementation guarantees that all the methods are going to be terminated in finite number of steps. That is wait-free implementation. Again, when we look at blocking-based implementations, okay, deadlock-free and starvation-free. In deadlock-free, actually, when we design a concurrent program without any deadlocks, usually we're going to call it a deadlock-free. Suppose if you maintain fairness among the threads, then it is called a starvation-free. That is the main difference between deadlock free and starvation free. Next one, when you look at the definition of the concurrent objects, okay, concurrent object is an object that can be concurrently accessed by several processes. Okay, nothing great in that. Okay, yes. Suppose to prove the correctness of any concurrent implementation, we are going to use the concept of linearizability. Okay. Yes. What is linearizability? Linearizability means actually particular implementation should satisfy two properties, two things. First one is sequential consistency. Second one is quiescent consistency. Sequential consistency states that threads are not allowed to reorder two invocations belonging to the same thread. Okay. Most probably, I will explain both of the things by considering a suitable example. Quiescent consistency states that threads are not allowed to reorder two invocations that are separated by the quiescent period. Quiescent period is a period during which processor is idle. That period is called quiescent period. Here to demonstrate that, here I consider a very simple example. Try to understand this particular example. Here X is a shared variable. Okay, we have two threads, thread A and thread B. When we look at this particular figure, okay, this particular one satisfies the quiescent consistency property, but not sequentially consistent. Okay, when we try to look at the reason for that, what may be the reason for this? Here, which one is the quiescent period? When you look at this is the quiescent period of the processor. Actually, this is the timeline. This is the timeline of the processor, right? This is the quiescent period during which processor is idle. Okay. Yes. When you look at this particular, these three operations, thread A performs x dot write. That means it is going to write 1 into the shared variable x. After that, it is going to perform the read operation. When it performs the read operation, it observes that value in that particular shared variable is 2. Okay, thread B is going to write 2. Okay, yes, when it is possible. When it is possible. Yeah, please unmute yourself. You can answer that particular question. Are you with me? Amit? Amit?
Yes, sir, I'm with you.
Okay. Can you try to answer this question?
No, sir, can you please explain it again?
Yeah. Right. Right. When we look at this particular statement, here these three operations are overlapping operations, right? That means thread A's operations write and read, and thread B's operation write. Okay, these three operations are overlapping operations. Actually, in concurrent context, these operations can be executed in any order. These operations can be executed in any order. In that context, suppose we can swap these operations of thread A. That means this can be performed first and this can be performed next. In that context, okay, we can observe this particular value, right? That means we can perform x dot write here. After that, we can perform x dot read here by thread A. After that, x dot write is going to be performed at this point. Yes, I would like to show that particular one in the next slide. Yes, when you look at this particular one, this is the point. This is the timeline, right? This is the timeline. In this particular timeline, first thread B is going to update the variable value in the variable x. That means thread B writes the value 2. when thread B writes the value 2 at this point of time, then this particular value can clearly visible to the thread A at this point of time, right? That means here, suppose when you look at this particular function, okay, read write function, actually you can observe it some line, right? That means here all method calls can be executed in that particular interval. You can think that this is a kind of interval. This is starting time, this is ending time of that particular function. This is starting time and ending time of that particular function. Okay, that particular function can be executed at any point in this particular interval. Right. Here in this context, suppose if thread B updates the value of the value of the shared variable at this point of time, after that thread A updates the value of that particular variable at this point of time, then thread A clearly sees that value 2. That means when thread A performs the read operation, it observes the value 2. After that, thread A writes 1 into that same shared variable. Okay. After some time, when thread A reads it, okay, it observes the value 1. Okay, right. When you look at the definitions of sequential consistency and sequential consistency, when you look at the definition of quiescent consistency, yes, threads are not allowed to reorder two invocations that are separated by the quiescent period. Here, this is the quiescent period. Okay, we are not going to reorder these things with these things. Okay, yes, all these operations are overlapping. These three operations are overlapping operations. If operations are overlapping in nature, these operations can be performed in any order. That is the quiescent consistency. When we think about sequential consistency says that threads are not allowed to reorder two invocations belong to the same thread. So when you look at this particular problem, it violates the sequential consistency. Why it violates the sequential consistency? For a particular thread, okay, it swaps the two operations, right? Actually, as per the problem statement, okay, initially thread A performs the write operation. After that, it is going to perform the read operation. Okay. When we look at the solution to this particular problem here, yes, these operations are interleaved in some order. Okay, if these operations are interleaved some order, here what we observed that, okay, within the thread A, read operation is performed first. After that, it is going to perform the write operation. That means within that particular thread A, those two operations are swapped. Okay, as per the definition of sequential consistency, that kind of swap operations are not allowed to reorder two invocations belong to the same thread. That is why when we look at this particular execution, it satisfies the quiescent consistency property, but not sequential consistency property. So this is quiescently consistent, but not sequentially consistent. Are you able to understand this? Are you able to follow this?
Sir, I had a doubt in this.
Yeah, please go ahead.
Sir, thread A, if we talk about that, then
yes,
first we'll have x dot read 2, then x dot write 1, then x dot read 1, right? Like in the same sequence, whatever be the interleave.
Yeah, this is the initial slide, right?
Yes, sir. So
okay,
in that case, like the processes belonging to thread A will not be swapped like in themselves.
No. This is the quiescent period, right?
Yes,
this
sir.
is the period during which processor is idle. Okay.
Yes,
actually, forget about sequential consistency. Here, I'm not going to discuss sequential consistency. From the quiescent consistency point of view, okay, these three operations are overlapping operations.
Okay.
These three operations are going to be submitted to the queue.
Yes, sir.
Okay. Yeah. Suppose consider that we have a single thread processor. All these operations submitted to a queue. Okay. During the execution, these operations can be interleaved in any order.
Yes, sir.
Okay. If some execution, right, satisfies that kind of property, that is called quiescent consistency.
Okay.
Yeah, as per the definitions, these three operations are overlapping operations because here processor is not idle. From here to here, continuously processor is busy, right?
Yes, sir.
Because from here to here, this operation is there. From here, next operation is started. From here, so from here to here, processor is idle. Processor is busy. During that time, thread A submitted 2 jobs. Thread B submitted 1 job. Right? These 3 jobs can be interleaved in any order. Okay, that is about quiescent consistency. Okay.
Yes, sir. Got it.
Yeah, in that context, thread A's operations can be executed in any order. Here we don't bother about first write operation should be performed, after that read operation should be performed. Here we don't bother about order of a particular thread.
Okay. Okay. Yes, sir.
Okay,
Yeah.
and we don't bother order of a particular thread. Right, in that context, x dot read operation can be performed first. After that, say that particular thread A can perform the write operation. In that context, we can observe, thread A can observe this particular x dot read one. That means when it performs the read operation on particular shared variable x, it observes 1. Otherwise, there is no possibility, right?
Yeah, yes, sir. Right.
Otherwise, there is no possibility, right? Okay.
Yeah.
Yeah. So in that context, I suppose based on the definition of quiescent consistency, yes, when we swap the operations of thread A, it satisfies. Yes, we can observe the x dot read at some point of time. X dot read equal to 1 at some point of time, right?
Yes,
Are you
sir.
with me? Okay.
Yes, sir. Got it.
Next. Here we can clearly observe that this kind of execution does not satisfy sequential consistency. Why? Sequential consistency says that not allowed to reorder 2 invocations belonging to the same thread. Here we reordered, right? That reordered the execution of thread A. That is why this execution does not satisfy a sequential consistency property. Next one. In the next example, I would like to show an example. This particular example satisfies the sequential consistency property, but not quiescent consistency property. See why. Please think about this particular one. Here, when you look at this particular problem, these periods are the quiescent periods. When you look at this is the timeline of the processor. Okay, this is the timeline of thread A, this is timeline of thread B. Okay, thread A performs the write operation during this particular interval. After that, this particular one. Here thread B performs the write operation here, right? So which periods are the quiescent periods here? This is one quiescent period. Okay, this is another quiescent period. These are the 2 quiescent periods, right? During which processor is idle. During which processor is idle. So this actually what I stated, I stated that this particular execution satisfies the sequential consistency property, but not quiescent consistency property. How? How?
And sir, because like the interval between x dot write 1 and x dot write 2, that is the idle period for the processor, and you'll have to swap between.
No. In sequential consistency, we are talking about within a thread. Sequential consistency speaks about it is not allowed to reorder 2 invocations belong to the same thread. Okay, sequential consistency does not talk about the across the threads, right?
Yes, yes, okay, got it. Like that, first write should happen and then read.
No, if that is the case, yes, we can push x dot write to the extreme, right? X dot write of thread B to the extreme, right?
Yes, sir.
Then, yeah, first in that context, we are going to perform x dot write of thread A. After that, x dot read of thread A. Later, some point of time, we are going to perform x dot write of thread B. Here in that context, what is going to happen? Here, this violates quiescent consistency property. Why it violates quiescent consistency property? Because this is the quiescent period. This is the quiescent period. Okay, during which processor is idle. Okay, here what we did, okay, we performed the x dot write operation after some time. We push towards write. In that context, what will happen? We violated the conditions of violated quiescent consistency property. What is quiescent consistency property? Not allowed to reorder two invocations that are separated by the quiescent period. Yes. But actually here, what will happen? This x dot write is performed after this particular quiescent period. This is quiescent period 2. This is quiescent period 1. Okay. This actually, to find the solution to this particular problem, this x dot write is performed at this point of time. In that context, we violated the quiescent consistency property. Are you with me? Are you
Yes,
with me? Yeah. So this, when you look at this particular example, okay, it satisfies the sequential consistency property, but not quiescent consistency property. Right. But when we look at the concurrent executions, okay, a concurrent execution should satisfy both. Then only we can say that that particular execution is linearizable. Otherwise, we cannot say that that particular execution is linearizable. Okay, if it is linearizable, then only our concurrent execution is correct. Otherwise, there is a problem with our execution. Right. Linearizability is sequential consistency plus quiescent consistency. That means it satisfies both the properties. Consider this particular example. Here we have 3 threads: thread A, thread B, and thread C. All these threads are working on the same shared variable x. Okay. Can you be here? This is the quiescent period. This is the quiescent period. Yes, during this time, actually, all these threads, okay, overlap each other, right? That means these operations can be executed in some order. Okay, one of the orders satisfies this particular execution. That is okay, right? In that context, how many possible orders we can get it? We can get it factorial 3 ways, right? 3 factorial ways, right? 6 ways. So one of those 6 ways satisfies this particular one. That is enough. In that context, in which way it can be executed? Do you have any idea?
X dot write 1, X dot read 1, X dot write 2, X dot read 2.
Yes, actually here we are going to perform x dot write 1. Here we are going to perform x dot read 1. Here we are going to perform x dot write 2. Here we are going to perform x dot read 2, right? That's enough, right? Are you with me?
Yes, sir.
Okay. Then that is about linearizability. Are you with me? So suppose if you write any concurrent program, okay, that concurrent program should satisfy these 2 properties: sequential consistency property or quiescent consistency property. Then only that is a valid concurrent program, otherwise not. So when we go back to the previous slide, now actually this linearizability gives the correctness condition for concurrent objects. Okay. Yes. In that particular linearizability, we are going to deal with linearization points of each operation. Suppose if we consider a particular data structure, on that particular data structure, we are going to perform some set of basic operations: insert, remove, and contains operation. In that context, we have to give linearization point of each operation. What is linearization point? Linearization point, LP is a point at which changes made by the one thread are visible to the all other threads. That is linearization point. Okay. Most probably I will explain those linearization points while discussing programs. Next one, synchronization techniques. Right. Why do we need synchronization? We need synchronization to avoid data races. We need synchronization to avoid data races. So, when someone asks what is the definition of synchronization, synchronization is a mechanism. It ensures that two or more concurrent processes or threads don't simultaneously execute a critical section. That means two or more concurrent threads should not be in the critical section. Okay, that is the concept of synchronization. Okay, yes. How can we use that particular synchronization while solving a particular problem? Here, I would like to explain all these 5 techniques by considering very simple data structure linked list. Okay, here I would like to discuss about 5 different synchronization techniques. They are coarse-grained synchronization, fine-grained synchronization, optimistic synchronization, and lazy synchronization. Yes, at the end, I would like to discuss non-blocking synchronization. That means without using locks, okay, how can we develop a code for a particular data structure? Okay, as the name itself, coarse-grained synchronization means we are going to acquire the lock on large chunks of the data. That is coarse-grained synchronization. In fine-grained synchronization, we are going to acquire the log on small chunks of data. That is fine-grained synchronization. When we look at the optimistic synchronization means actually to perform the required task with the help of minimum number of logs. That means to perform a particular task by acquiring the lock on minimum number of nodes. We can say that. Okay. Next one is lazy synchronization. Lazy synchronization means we are going to postpone the hard work. Okay. Suppose if we consider delete operation of a binary search tree. Okay. Yes, delete operation little bit costly operation, right? In that context, initially what can we do? We can logically delete a particular node from the tree. After that, we can physically delete that particular node from the tree. Okay. That means we are going to postpone the hard work. Okay. That is lazy synchronization. Actually, to get the better performance, lazy synchronization helps us a lot. Finally, I'm going to discuss non-blocking synchronization. In the non-blocking synchronization, how can we write or how can we develop a code for a particular data structure without using locks? For that, we are going to use, yesterday, Dr. Saurabh discussed about CAS, compare and set, and something actually atomic operations, right? Those atomic operations are LL and SC, load linked and store conditional, such type of operations, we can use it. Next one. Yeah, when we look at the coarse-grained synchronization, here, what can you observe from this slide? What can you observe from this slide? What kind of data structure it is?
A linked list.
Yeah, this is a linked list. Okay. When we look at this particular linked list, you can find 2 sentinels, right? Head and tail. After that, what can you observe? How the values are arranged in that particular linked list? All the elements in that particular list are in sorted order. Okay. Right. Here, there are 2 threads, thread A and thread B. Okay. Thread A wants to perform insert operation. Thread B wants to perform delete operation. In that context, when 2 threads containing, okay, then somehow thread A acquired the lock on node head. Okay. Right. When it acquires the lock on node head, okay, it performs the required operation and releases the lock and releases the lock. Now, thread B acquires the lock on head and performs the required operation, releases the lock. So what is the problem with this particular implementation? Why it is called coarse-grained implementation? Why it is called coarse-grained implementation? Do you have any idea? Coarse-grained stands for we are going to acquire lock on large chunks of the data. We are going to acquire the lock on large chunks of data. Okay. Are you with me? Hello.
Yes, sir. So like because the whole linked list can be reached if we have a lock on that.
Yeah, when suppose if you lock the head node, okay, no other thread can access any one of the nodes in the particular linked list. Okay, suppose when you look at this particular problem, okay, insert of 35 is going to work at node 30, and delete of 10 is going to be between head and node 10 and 20, right? Suppose when the node 10 is deleted, only these two nodes are going to be affected, head 10 10. When we try to insert 35, only node 35 is going to be 30 is going to be affected, right? In that context, these two operations are non-overlapping in nature. Are you with me? In that context, these two operations are non-overlapping in nature. If two operations are non-overlapping in nature, these two operations can be performed at the same point of time. But when we use the concept of coarse-grained synchronization, thread B is unable to acquire the lock on the required set of the nodes, and in turn, it is unable to perform the required operation. That is the problem. Okay, so when we look at the drawbacks of this particular one, okay, what are the drawbacks of this particular coarse-grained implementation?
Two jobs which are non-overlapping cannot occur simultaneously.
Yeah, actually, it creates a sequential bottleneck at the sentinels, right? Suppose if the levels of the concurrency is high, it creates a sequential bottleneck. Okay, when it is good, when hi, sorry for this. Today we had very heavy rain in Hyderabad, and that is why we had power issues. Are you able to hear me?
Yes, sir.
Okay. Sorry for that. When we look at the fine-grained synchronization, yeah, in the fine-grained synchronization, we are going to acquire the lock on small chunks of the data. Assume that here we are going to acquire the lock at the node level. Earlier in coarse-grained synchronization, we are going to acquire the lock at the object level, right? for the entire list. Here we're going to acquire the lock at each node. Suppose if you want to perform the insert operation, okay, how it can be performed? Yes, head is not the required node. If head is not the required node, then what will happen? Then you try to acquire the lock on 10. Okay. After that, releases the lock from the head. Yes. After that, it acquires the lock on 20 and releases the lock from 10. After that, it acquires the lock on 30, releases the lock on 20. Okay. It uses kind of hand over hand locking mechanism. After that, when thread A acquires the lock on the required node 30, okay, thread B acquires the lock on the required set of nodes. Okay, thread B acquires the lock on the required set of nodes. So in that context, thread A and thread B both can perform their operations at the same point of time. Both can perform their operations at the same point of time. Okay. Yes, when we use the fine-grained synchronization, what can we observe this? This is a kind of blocking-based implementation, right? Blocking-based implementation. Suppose due to some reason, if thread A is delayed, all its subsequent threads also going to be delayed, right? Because reason behind that is it uses kind of hand over hand locking mechanism. That is the problem with this fine-grained synchronization. Yes. Do you find any other issues with this fine-grained synchronization? Do you find any other issues with the fine-grained synchronization?
It might take time to find the right location, like shifting the locks.
Yes, actually, somehow it is correct. It may take some time to identify the required set of nodes. Okay, that is good. Not only that, here, is there any possibility to get the deadlock? Suppose if someone acquires the lock in a different order. In here, we trying to acquire the lock from the left to right, right? Instead of that, suppose one thread acquires the lock from left to right, another thread acquires the lock from right to left. In that context, there is a possibility of deadlock. Are you with me?
Yes, sir.
Is there any possibility? Yes, there is a possibility, right? Okay, suppose I assume that. In that context, we have to be very careful. Okay, because not only that, okay, here we are working with, we are going to log the nodes. When we try to log the nodes, actually, if we forget to unlock it, then that particular node is not accessible to any other thread. That particular node is not accessible to any other thread. Again, that creates a problem. So when we are developing a solution to a particular problem by using the fine-grained synchronization, we have to be very careful. We have to be very, very much, okay. Otherwise, we end up with deadlocks, or some nodes may not be accessible. Sometimes we will get incorrect results. Okay, many things will happen. That is why we have to be very careful while developing a solution to a fine-grained synchronization. Not only that, here when we look at that particular traversing mechanism of thread A, here thread A uses hand over hand locking mechanism. When you look at the hand over hand locking mechanism, what is hand over hand locking mechanism? See, first of all, a required node for thread A is node 30. How it reaches to the node 30? It reaches to the node 30. First, it activates the lock on head. Later, it activates the lock on 10. Then only it releases the lock on head. After that, it activates the lock on 20. After that, then only it releases the lock on 10. After that, it activates the lock on 30. Then only it releases the lock on 20. 30 is the required node for thread A. Okay, that is a kind of hand over hand locking mechanism. Okay. Yes, suppose due to some reason, this particular thread is delayed, all other subsequent threads are going to be delayed. Okay. That is a kind of a blocking based implementation, right? Okay, blocking based implementation. Yes. Suppose if you want to observe, or if you try to get better speed ups or better throughput, okay. Yes, we try to stop this kind of blocking based mechanisms, right? We have to write a code for non-blocking implementations, that is a kind of lock-free methods. Okay. Yes, developing a lock-free method is lock-free implementation is everyone can appreciate it, but writing the lock-free methods, okay, we have to put so much effort. Next one is optimistic synchronization. In optimistic synchronization, yes, here uh, we are identifying the required set of nodes without using hand-over-hand locking mechanism. That means, suppose if thread A wants to perform insert operation, straight away we are going to that particular node, a simple traversal without acquiring any locks on that path from the head node to that particular node. Once we identify the required node, okay, we try to acquire the lock on node 30. Okay, once node lock is acquired, we are going to verify that whether that particular node is reachable from the head node or not. Okay, whether that particular node is reachable from the head node or not. That is why it is called optimistic synchronization. Okay, yes. When we look at after acquiring the locks, okay, we are going to validate whether that particular relation holds or not. If particular relation holds, then we can comfortably perform the operation. If particular relation does not hold, then we have to again retraverse from the head node and identify the required set of nodes. So when do we consider this particular optimistic synchronization? Do you have any idea? When we look at this particular solution, okay, how do we acquire the locks in the optimistic synchronization? First of all, when you look at this particular problem, there is a linked list. Okay, linked list consists of some set of nodes. Here, thread A performs the insert of 35, thread B performs the delete of 10. Okay, in that context, how are you going to acquire the lock on the required set of the nodes? First of all, by using simple traversal technique, we are going to identify the required set of nodes. Okay, for thread A, we acquired the lock on node 30. We acquired the lock on node 30. Oh, sorry, first of all, the thread A, we reaches to the node 30. Once we reaches to the node required node, yes, then we are going to acquire the lock on that particular node. Then we are going to acquire the lock on that particular node. Once lock is acquired, okay, again, we are going to verify it, whether that node is part of the list or not. Sometimes some other thread may delete that particular node. In the concurrent execution, some other thread may delete that particular node 30. Okay, then in that context, we have to cross-check it. Suppose if you use the fine-grained synchronization, there is no need to cross-check it, right? Here, how do we cross-check it? Again, we are going to traverse it from the head node. Are you with me?
Yes, sir.
Okay. So here, so when do we consider this kind of optimistic synchronization? When do we consider this kind of optimistic synchronization? This kind of optimistic synchronization is worthwhile only if it succeeds more often than not. Okay, that is the case. Okay, suppose when we retraverse it, we observe we are unable to reach that particular node. In that context, what will happen? All our previous effort is going to be wasted, right? That is the problem. At the same time, we need to retraverse at least twice. Suppose if length of the linked list is very high, retraversing twice is a very costly affair. Are you with me?
Yes, sir. So like there should be less deletions, like there should be less anomalies.
Yes, that's true. That's true. Next one is lazy synchronization. When you look at the previous data structure and this one, did you find any difference? When you look at the previous one, previous also there is a linked list. This is also linked list. There is a small difference between previous one and this one. What is that?
There is one more field with a number.
Yeah, one more field with a number. Okay, we can consider that as a flag field. We can consider that as a flag. If flag value is 1, then we can think that that particular node is in the list. If flag value is 0, then that particular node is logically deleted from the list. Later, after some time, we are going to delete that particular physically from that list. Okay. Yes. Suppose here I would like to explain by considering a very simple example: delete operation. Suppose if you want to perform delete operation, delete of 10. To perform a delete operation, we need 2 nodes. Okay, predecessor and the required node. Which node is going to be deleted? So in that context, we are going to log head and node 10. When we log head and node 10, what will happen? Yes, this is a kind of deletion. In that context, first we are going to logically delete this particular node. How are you going to logically delete this particular node? Initially, we are going to set the flag value of node 10. When we set the flag value of node 10 to 0, means that that node is logically deleted from the node, from the list. Means that that node is logically deleted from the list. Once that node is logically deleted, we can use that node for the traversing purpose. Remaining threads can use that particular node to reach all other subsequent nodes, right? Okay, are you with me? Next
Yes, sir.
one, next one is we are going to delete this particular node physically from the list. Okay. Yes, physical deletion logic is very simple and straightforward. We can delete it and releases the lock. Okay. Advantage of this particular one is actually physical deletion is more costly operation as compared with logical deletion. Okay. In that context, that particular logical deletion is performed first. After that, physical deletion can be postponed. We can postpone some other same thread or some other thread can delete that particular node physically from the data structure. That is the advantage of lazy synchronization. Usually, to get the better throughput, most of the people consider this lazy synchronization. Most probably, I'm going to show an execution of a linked list. Okay, in that also you can observe better performance when we consider this lazy synchronization mechanism. Next one is non-blocking synchronization. When we look at this particular non-blocking synchronization, that means here we are going to use some other operation, that is compare and set. Yesterday, actually, Dr. Saurabh discussed about CAS operation, right? Compare and set. Okay. When you look at this particular compare and set operation, it takes 3 values: actual value, expected value, and updated value. Okay, update value. If actual value is equal to the expected value, okay, then we are going to replace actual value with update value and return true. Otherwise, we are going to return false. Okay, that is simple CAS operation. Okay, how this particular one is going to be performed? This is going to be performed by using atomic instructions of the processor. Each processor gives some set of atomic instructions, right? By using those atomic instructions, we can compute this particular operation. Okay. Right here, when you if you want to delete 10, in that context, what will happen? First, we are going to logically delete 10. Okay. Yes, by using simple CAS operation. Later, we are going to delete. We are going to physically delete that particular 10 by using another CAS operation. So here, to perform a delete operations, we are performing 2 CAS operations. One is for logical deletion, and second one is for physical deletion. Once it is logically deleted, we don't bother about it. Okay, later after some time we can physically delete it. Same thread or some other thread can that node can physically deleted from the list. That is about different synchronization techniques. Are you able to follow these 5? Here we discussed about 5 types of synchronization techniques. They are coarse-grained synchronization, fine-grained synchronization, optimistic synchronization, lazy synchronization, and non-blocking synchronization. Right? Okay. Next, we are going to use these synchronization techniques with the help of some data structure. Okay, we try to understand all these synchronization techniques by the help of some data structure. Okay, usually such type of data structure is called a concurrent data structure. Okay, here first of all, I would like to give the definition for a concurrent data structure. In a shared memory environment, a data structure which supports concurrent execution of multiple threads of computation is called a concurrent data structure. Okay, this is a shared memory environment. In a shared memory environment, we have a particular data structure. Here you can find a tree data structure. Need not be a tree. Suppose if you have a linked list, okay, or some other data structure. In a shared memory environment, if you have a data structure which supports concurrent execution of multiple threads, okay, that data structure is called a concurrent data structures. That data structure is a concurrent data structure. Okay, today I would like to explain about concurrent implementation of linked list by considering these 5 synchronization techniques. By considering these 5 synchronization techniques. Till now, do you have any doubts? I would like to clarify your doubts. Do you have any doubts? Please unmute yourself. If you have any doubts, please express your doubt. Sir, could you explain it once? What is that? Pooja. Pooja, please unmute yourself. Hello. Pooja. Pooja Bharadwaj. Yes. Hello. I'm unable to hear you. Yes. Now, I would like to show the demonstration on linked list program by using linked list program. Are you able to see the screen? Rishikesh?
Yes, sir.
Okay. I think I shared this code with you, right? You can download it from that particular shared folder, right?
Yeah, it is.
Yeah, it is there. When I look at, first of all, I would like to explain coarse-grained synchronization. Yeah, course list.java. When you look at this particular one, here, what can you see? Here I used a lock, right? Why do we need lock? Why do we need lock? Why do we need lock? We need locks to achieve synchronization among the threads. We need locks to achieve synchronization among the threads. Or to avoid data races, we need locks. Okay, right. Lock is a kind of synchronization primitive. Yes, to solve this particular problem, I used the reentrant lock. Reentrant lock is available. Reentrant is a kind of lock that is available in util package java.util.concurrent.logs. Okay, and lock is the interface. When we create an object of reentrant lock, that can be assigned to the base class, object of the base class. Here, when you look at this particular statement, what is the statement? Yes, we are creating an object of type reentrant lock. We are assigning that particular object to the lock. Lock is of type lock. Lock is a of type lock. Here, reentrant lock. Here, this particular lock is a base class, and reentrant lock is a derived class. Right? We can assign the object of the derived class to the base class. Next one. When we look at this particular course list, okay, what can you observe here? Here he can observe that head, tail. Head and tail are the sentinels. Right. After that, when you look at the constructor of this particular class, what can you observe? Here we created two nodes. Okay. Those actually one node is initialized to assigned to the head, another node is assigned to the tail. At the end, okay, we created, we wrote a statement that is head next equal to null, right? Sorry, head next equal to this dot tail. Fine. When you look at the line number 13, you can find that. Are you able to understand that particular constructor? Nothing great in that. Okay. That means here we are creating a simple sorted list, sorted linked list. For that, sentinels, that head is initialized with integer dot minimum value and tail is initialized with integer dot maximum value. Okay. And head dot next equal to this dot tail. In that context, all the values between this integer dot minimum value and integer dot maximum value. Are you with me?
Yes, sir.
Okay. Next, after that, when you look at this particular one, okay, that is class node. Okay. Yes, you can find two data members. What are they? One is key and second one is next. Next holds the address of node. Next holds the address of the node. When you look at the constructor of this particular private class, this is an inner class. This is an inner class. This is a class within a class. What is the scope of that particular class? Scope of this particular inner private class is within that particular outer class. Next one is here, when you look at this particular constructor, node of int item, this dot key equal to item and this dot next is null. I think this particular class, you can easily understand the purpose of this particular one. Are you able to follow now? Do you have any doubts? I would like to clarify your doubts. Just now I saw you. Okay, fine. Now, usually here we are going to perform three operations on this particular list. They are add, remove, and contains. These are the basic operations. Okay. All these basic operations return true on successful case. Okay. And false on unsuccessful case. Returns true on successful case and false on unsuccessful case. That is why when you look at this particular return type of this particular method, add method, Boolean. Similarly, remove method, return type is also Boolean. Contains method also, similarly for contains method, return type is Boolean. Right. Next, you know how to perform, such operation on a linked list. How do we perform such operation on a linked list? We start at the head node. If head is the required node, okay, then we stop at that node itself. If head is not the required node, with the help of the next field, we go to the next node. We are going to verify it, whether the next that particular next node is the required node or not. If next node is not the required node, then again we go to the next node. Again, in that way, we are going to identify the required node, right? Once we identify required node or required set of nodes, perform the operations with that particular required set of nodes. Are you with me? That is very simple and straightforward. I think great in this. Okay. Here, I would like to explain one of these three methods. I think then you'll be more comfortable. When you look at, forget about this line number 25. Line number 25 is the lock method that is used to acquire the lock on this object. That means current object. When you look at these lines, okay, here we consider two variables, predecessor and current. Okay, initially predecessor is head, current is predecessor next. After that, we are going to verify while current dot key is less than key, then predecessor equal to current, current equal to current next. When would we come out from this particular while loop? When would we come out from this particular while loop?
When the key is more than the key.
Yes. If key dot current dot key greater than or equal to key, we come out from that particular while loop, right? Okay. So in that context, there are two cases. If key dot key equal to current key, that means already required key is already present, then there is no need to insert it. In that context, it returns false. Assume that here we are implementing a set. Okay, set implementation. We're doing a set implementation. In that context, if key dot key equal to current dot key, return false. Else, here what are we doing? We are creating a new node with the required value. Okay, that is going to be stored here. After that, this node next equal to current, and predecessor is node. Predecessor next is node. Then return true. Are you able to understand this particular logic? Do you have any doubt? I would like to explain that particular logic by considering a very simple example. Because you may know that logic, but you may forget, right? Because you studied those linked list concepts way back in the first year and second year of BTech, right? Or MCA or some other course. Are you able to follow? Do you have any doubts? Hello? Yes?
Yes, sir. It's clear.
Okay, right. Next. When we look at this particular one, in the coarse-grained synchronization, we are going to acquire the lock on large chunks of the data. If we acquire the lock on large chunks of the data, that means we are going to acquire the lock on the whole object. Okay, that means whole list. In that context, what are we doing here? Here, for the course list, lock is a member of this particular course list object, right? Lock is a member of this particular course list object. Okay. Then here we are going to initialize this particular lock with new reentrant lock. Okay, reentrant lock has some methods, right? What are those methods? Okay, with the help of that, we can lock it and unlock it. Okay. When we call this particular lock.lock, what will happen is it acquires the lock on this particular whole object. That means here we are going to acquire the lock on entire linked list. Here we are going to acquire the lock on entire linked list. Once we acquire the lock on entire linked list, no other thread will be allowed into the particular linked list to perform any other operation. No other thread will be allowed into the particular list to perform any one of the basic operations. Only thread which acquires the lock or only thread which acquires the lock can perform the required operation. Are you with me? Are you with me?
Yes, sir.
at the end, what will happen? Once it performs the required operation, okay, finally block is going to be executed. In that finally block, we are going to call lock.unlock. That means we are going to release the lock. Once it releases the lock, yes, now that object is free. Okay, and, no thread acquired the lock on that particular object. Now all the remaining threads, okay, can try to acquire the lock on this particular object. If one of those remaining threads succeeds, that particular thread will be allowed to perform the operation on that particular list, perform the operation on that particular list. Okay, similarly, that is the insert method. Similarly, remove method. When you look at the logic of the remove method, it is very simple and straightforward. Forget about this lock and unlock. This is the logic of remove. Okay, what is the logic of remove? Try to understand this particular logic. Initially, predecessor equal to this dot head. Head is initialized with predecessor variable. Current equal to predecessor next. Okay, now predecessor points to the head and current points to the head next. After that, we consider the logic. While current dot key less than key, predecessor equal to current equal to current next. When would we come out from that particular while loop? If current dot key greater than or equal to key, then would we come out from that particular while loop. Okay. After that, this is a remove operation. To perform a remove operation, required key should be present in the list. Then only we can remove it. Otherwise, we cannot remove that particular one from the list. Okay. If required key is not present in the list, then it is unsuccessful case. If required key is present in that context, what are we doing? We are going to doing predecessor next equal to current next. Predecessor next equal to current next. In that context, that particular current node is going to be deleted from the list. That particular current node is going to be deleted from the list. On successful deletion, it returns true. Okay. Else, suppose if we consider unsuccessful case, it returns false. Unsuccessful case, it returns false. Are you able to understand this? Do you have any other doubt? Any doubts? Do you have any doubt? I hope that you are able to follow this, right? Nitin Singh. Nitin. Pranod. Pranod Kumar. Hi, Pranod. Are you able to hear me? Renuka? Renuka?
Yes, I am able to hear you.
Okay. Do you have any doubts?
I'm trying to understand.
Okay. Yes. No doubt. Okay, fine. So this is about the remove method. Yes, to perform this remove method, here we consider the coarse-grained synchronization, right? In the coarse-grained synchronization, we are going to acquire the lock on whole object, right? Entire object. That is why here, before going to execute all these statements, we call this particular statement that is lock.lock. With the help of this, we are going to acquire the lock on this object. Okay. Finally, once we perform the required task, this finally block is going to be executed. In the finally block, we are going to remove that particular lock. Remove that particular lock. Next one is contains method. Similarly, contains method. Here, unsuccessful case, return the key equal to current dot key, it returns true. In unsuccessful case, that particular statement returns false. Nothing great in that. Okay. Here also we are going to use same thing, lock.lock. Okay, once we come out from that particular one, finally we are going to call lock.unlock. Are you with me? Yeah, here you can find one more method. If you want to print it on the screen, you can use it. Okay, at this point of time, I'm not going to print the entire list on the screen. If you want, you can try. Okay, yes. I think now you are able to understand this particular course list implementation, right? Now we are able to understand this particular course list implementation, right?
Yes, I got it.
Okay, right. Now, I would like to open this wrapper class, list test. Yes. When you look at this particular list test class, here it takes some arguments. What are those arguments? This is the constructor of this one, number of threads. Okay, how many number of threads you want to launch, and range. Okay, the range of the keys you want to store in the particular list. Okay, after that time, how much time you want to execute this particular one. Prefill. Suppose to measure the performance, we cannot test the throughput on the empty list or list with some number of values. Okay, suppose at least data structure should be considerable amount of size. Then only we can run these parallel programs or concurrent programs. We cannot run these parallel or concurrent programs on small data structures with 10 nodes or 20 nodes. Suppose if you want to test it, actually create a data structure with 1,000 nodes, okay, and try to perform the this test operation, okay. Next, this is the prefill. We are going to prefill that particular data structure with some number of nodes. After that, yes, usually what are the operations are we going to perform on this particular data structure? We are going to perform 3 kinds of operations. Okay, that is contains operation, insert operation, and remove operations. Okay, yes. Suppose if you are going to perform 100 operations, okay, how much percentage of operations are contains operation? How much percentage of operations are insert operations? How much percentage of operations are the delete operations? Suppose in this context, if I gave this particular S limit as 50, okay, means that, okay, 0 to, suppose initial value is 0, and this is not a prefill. Initial value 0 to 50, that means 50% of the operations are the contains operations. Next, if I give this I limit, that is insertion limit, is 75, means that when we look at the difference between 50 and 75 is 25. That means 25% of the operations are the insert operations. All remaining operations are the delete operation. That means 25% are the delete operations. Okay. While executing this program, I would like to give the input as, this is the command prompt, 1. 1 is the number of threads. After that, range. Suppose if I give range as 2000, that means I'm going to store the values from 1 to 2000. Time. If time is time in milliseconds, if I say that 10,000, means that this program is going to be executed 10 seconds. This program is going to be executed 10 seconds. Next one is prefill. If we are going to prefill this particular data structure with 50% of the elements. 50 means we are going to prefill this data structure with 50% of the elements. Here range, number of range of this particular one is 2000, right? In that context, 50% means half of it. That means we are going to prefill that particular entire list with 1,000 nodes. Next, after that, if I provided 50, means that 50% of the operations are the contains operations. If I provided the value 75, means the difference between 50 and 75, that is 75 is the S limit. Difference between these two is 25. So 25 are the insert operations. Remaining 25 are the delete operations. This is the workload of this particular one. Okay. Workload of this particular execution is 50, 25, 25. Means that 50% of the operations are the contains operations, 25% of the operations are insert operations, and remaining 25% of the operations are the delete operations. Okay. That is the meaning of this particular input. This first argument is the number of threads. Second argument is the range of the keys. This is how much time you want to execute this particular program. Okay, a prefill percentage. Are you going to prefill with 50% of the elements? Okay, suppose if you want to, you can vary 50 or 70. If you want to prefill with 30%, you can do that, no problem. Next, after that, this 50 means, okay, 0 to 50, that means 50% of the contains. 50 to 75 means the difference is 25. So 25% of the operations are the insert operations. Remaining 25% of the operations are the delete operations. Are you able to understand the input?
Sir, prefill is done with random values.
Yeah, prefill is done with random values between 1 and 2000, 20,000, 2000.
Okay, sir, got it.
Okay. Right. Right. After that, when you look at this particular one, these are the command lines. First one is the number of threads, range, time, prefill percentage, S limit, and I limit. Okay. Once we read all these values from the command lines, we are going to create an object with these values. Okay. After later, we are going to call this prefill method. We are going to prefill the data structure. Later, we're going to call ob.testParallel. That means parallel execution of this particular one with the help of required number of threads. Okay. Later, we are going to calculate throughput. To calculate throughput, we are going to calculate the total number of operations with the help of ob.total operations. Total number of operations is going to be recorded in this particular variable, total operations. Later, we are going to measure throughput in terms of millions of operations per second. Millions of operations means total number of operations. We have to divide that total number of operations with this one, right? 1 million times actual time. Okay. And then what do we get? Then what do we get?
How many million operations are done in 1
second? This is the million operations per milliseconds up to this point. Because the time is in milliseconds, right? We are going to provide the time in milliseconds. That is why we multiplied this particular one with 1000. Otherwise, there is no need to multiply. Okay. Here we are going to measure millions of operations per second. When we consider this particular expression, we will get throughput per millisecond. Throughput per millisecond. Suppose if you want to measure throughput per second, we have to multiply this whole value with 1000. Then only we will get throughput per second. Are you with me? Are you with me?
Yes.
Okay. Later we are going to print this whole all things on the screen. That's it. Nothing great here. When you look at this particular one, here initially I considered course list. This is the course list. And this is the instance of that particular course list class. Now, Java list test.java successfully compiled. After that, Java list test. What is the first argument? First argument is the number of threads, 1. What is second argument? Range of the keys, 2000. What is third argument? What is third? Time. How much time you want to execute? 10,000 milliseconds. Next argument is prefill percentage 50. Okay, next argument is percentage of contains operations 55. Okay, next insert operation, remaining are delete operations. When we consider the number of threads is 1, we observe this much throughput. What is the throughput? It is 0.54 millions of operations per second. 0.54 millions of operations per second. Suppose here in this particular implementation, we are going to increase the number of threads. When we try to increase the number of threads, let us see what will happen. When we increase the number of threads, we are expecting that we're supposed to get the better performance, right? We are expecting that we're supposed to get the better performance, but here we observed that we never got the better performance. What may be the reason for this?
Maybe the coarse-grained implementation.
Because of the contention, because these threads creates a contention at the head node. Because of that, we observe the less throughput. Because of that, we observe the less throughput. C. As we increase the number of threads, it creates the contention. We never get any extra benefit with the help of concurrent program. So actually, for a little bit understanding about the concurrent programs, we can consider coarse-grained implementation. Okay. Actually, no one will consider a coarse-grained implementation of a particular data structure. Right? Okay. Are you with me? Do you have any doubts?
Yes, sir, but like, why is the throughput decreasing? Like, it should remain the same at least, right?
No. Actually, here, each thread trying to acquire the lock, right? When
Yes.
each thread trying to acquire the lock, suppose if multiple threads trying to acquire the lock, there should be a contention among them, right?
Oh, okay.
If contention among them, so many threads time, actually we are going to execute this particular program 10,000 milliseconds. During that particular time, if the threads waste their time to acquire the lock, okay, they cannot perform any useful work, right?
Yes, sir. Okay.
That is the problem.
Yes, sir. Got it.
Okay. How can we overcome that particular problem? To overcome that particular problem, okay, yes, we are going to consider fine-grained list implementation. Yes, VI fine list. When we look at this particular fine list implementation, okay, here also we consider reentrant block. For the sake of simplicity, I kept it reentrant block. Here you can use any other lock, no problem. If you want, you can use CLH lock or MCS lock or any other lock. You can use this TAS and TTAS. Many other locks are there. Here, when you look at the this particular one, when you look at the constructor of this node, what is there? What is there? Here, in the earlier program, we created an object of reentrant class. Earlier, we created an object of reentrant class, right? This is used to acquire the lock on the particular object. Okay, here we created a reentrant of that particular one. We are assigning that particular object to this this dot lock. Here, lock is a member of this particular private class node, right? This is another class.
Yes, sir. So each node will have its own block.
Yeah, actually, in that context, actually, suppose if you do the design in this way, in this fashion, what can we do? We can acquire the lock at the node level. Earlier, we are going to acquire the lock at the object level, right? That means entire list level. Here, we are going to acquire the lock at the node level. Are you with me?
Yes, sir.
Okay. Right. Next one. As usual, just like the previous program, here there is a constructor for this particular class, finalist. Here also we created two nodes. One is integer.minimum value, second one is integer.maximum value. Okay, here head is integer.initial value, head next is integer.maximum value. Okay, are you with me?
Yes.
Right, next one. Here also on this particular data structure, we are performing three basic operations. Those are add, remove, and contains. How that particular add operation is going to perform, I would like to explain one of those three methods. For me, it is difficult to explain all the three. Now I would like to explain one of those three. Remaining methods are similar to that. You can easily understand. When you look at this particular add method, we need predecessor and successor, predecessor and current. So initially, predecessor and current variables initialized with null. Later, okay, we are going to here, when you look at this particular one, okay, head.lock. When we look at this logic of fine-grained synchronization uses the hand-over-hand locking mechanism. Okay, did you remember that point? Fine-grained synchronization uses the hand-over-hand locking mechanism, right? That means when you look at this particular one, suppose if you want to, thread A wants to perform insert operation, okay, insert of 35. So required node for this particular one is 30. Okay, how it reaches to the 30? Pardon?
Screen is not visible.
Sorry. Okay, I think, is it visible?
Yes, sir.
Yeah. When you look at this particular fine-grained synchronization, actually here thread A wants to perform insert operation, insert of 35. To insert 35, first of all, it should identify the required node. Required node is 30. To reach to the required node, it uses the hand-over-hand locking mechanism. That means first initially it acquires the lock on head, later it acquires the lock on 10. 10 is not the required node. In that context, it has to release the lock from the head and acquires the lock on 20. Okay, and repeat that process. And when we repeat that process, it finds the required node 30. Once it finds the required node 30, performs the required operation and then releases the lock. Are you with me? In that context, suppose thread B wants to perform some other operation. Thread B wants to perform delete of 50. Okay, thread B cannot overtake thread A. Thread B cannot overtake thread A. Okay, this kind of implementation satisfies the FCFS, first come, first serve. Okay, thread which acquires the lock on the head. Okay, all other subsequent threads should follow that particular one. You should not cross that particular thread. Are you with me?
Yes.
Okay. Now, here we use the same logic. Initially, we're going to lock head.lock. When you look at the line number 23, you can find that. After that, we are going to assign predecessor value. Predecessor is head. Current is predecessor next. Okay. Current.lock. We are going to lock the current. Now predecessor and current are locked. Okay. After that, when you look at this particular logic, what is there in that? If current is not the required key, if current is not the required key, or if current is not the required node, then what should we do? We have to release the lock on head, right? Predecessor, right? And acquire the lock on the next node, right? Are you with
Yes.
me?
Yes.
So here what we did, here we did that actually we are releasing the lock on head or predecessor dot unlock. After that, predecessor equal to current. Okay, current equal to current next. Anyhow, we locked the current, right? So no one will modify this particular current. Where current is locked? Current is locked in the line number 27. Current is locked in line number 27. So here we did predecessor equal to current, current equal to current next. After that, now current next is not locked. That means the current is not locked. So we are going to lock the current now. Are you able to understand this particular logic? This is very, very important thing. This is the predecessor. This is the current. This is the current next. This is the predecessor. This is the current. This is the current next. Okay, initially we acquired the lock on this particular node. Later we acquired the lock on this particular node. Okay. If current node is not the node of interest, in that context, what should we do? We are going to release this particular lock. We are going to release this particular lock. This particular lock is going to be released. Okay, no more lock on this particular node. After that, we are going to lock this particular one current next. After that, we are going to lock this particular one current next. What's the logic for that? Logic is here simple. If current is not the current dot key is not the required key, then we are going to unlock the predecessor. That means predecessor dot unlock. Once we unlocked it, okay, then we are going to lock the current next. How do we lock the current next? We have to get that particular current next. Okay, in that context, what will happen? When we lock the current next, this particular current becomes the predecessor. This becomes the current. Logic is predecessor equal to current. So this current becomes the predecessor. Next current is current next. This node next is the current. And current dot lock. We are going to lock this particular one. Are you able to follow this?
Yes, I got it.
Okay. Now repeat this process. Okay. Yes. When would we come out from this particular while loop? We come out from this particular while loop if current dot key greater than or equal to key, then come out. If current dot key is greater than or equal to key, then we need to think about if current dot key equal to key, that means required key is already present in the list, then it is unsuccessful insertion. Then it is key is already there, then it is unsuccessful insertion, right? Then in that context, return false. Otherwise, if key is not present in the list, then what should we do? We have to create a new node with the required item. Okay, that is going to be assigned in that particular new node. New node next is current. New node next is current. Are you with me?
Yes, sir.
Yeah, predecessor next is new node. Predecessor next is new node. Return true and finally come out from this. Yes, finally release the lock. Current dot unlock. Finally release predecessor dot lock. Right. When we look at this particular logic, initially we are locking the predecessor. Later we are locking the current. While releasing, we are unlocking the current first. Later, we are releasing the procedure. Are you able to follow the order?
Yes, sir.
Yeah. Next one. Here, when you look at this particular statement, line number 40, yeah, I put a comment for that line number 40. What is that? LP of add method. That is linearization point of that particular add method. Linearization point means when that particular thread updates that particular one, predecessor dot next equal to new node. Okay, that particular new node is part of the list. Are you with me? After executing that statement, okay, that new node is part of the list. Otherwise, it is not part of the list. After executing that particular statement, then only new node is inserted into the list. Are you with me?
Yes, sir.
Yeah. So that is why that statement is called linearization point of add method. That statement is called linearization point of add method in successful case. In successful case, in unsuccessful case, anyhow, we're not changing the data structure, right? In that context, linearization point of unsuccessful case is either 35 or 36. Any line can be the linearization point of unsuccessful case. We can say that. Okay. Are you able to understand this particular add method?
Yes, sir.
Okay. Right. Similarly, delete remove method. Here for remove method, linearization point is here. Line number 66 is the linearization point for the remove method. Similarly, contains method. Contains method linearization point is 92. 92 is the linearization point of contains method. Right. Now we are going to execute this particular one. How do we execute this particular one? Vi list test.java. I'm going to comment this particular statement. Later, I'm going to compile this particular code. Successfully compiled. Again, first argument is the number of threads. Second argument is the range of keys. Third argument is the amount of time you want to execute. Fourth argument is the prefill. Fifth argument is the number of contains operations. Difference between fifth argument, sixth argument is the amount of insert operations. And difference between sixth argument and the 100 is the percentage of delete operations. Right? Here it is a workload. Okay. Suppose if you want to do the scientific computations, or if you want to publish the papers and data particular performance of particular data structure, you need to consider different workloads. Okay. Here I consider the workload 50, 25, 25. If you vary those values, you can consider different workloads. 0, 50, 50, or 100, 0, 0, 30, 35, 35. Just like that, you can get different workloads. When you look at this particular output, what can you observe? You can observe that you got the throughput 0.12. When you compare the throughput of course list and throughput of this fine list, throughput gives the better throughput. Okay, that for course list gives the better throughput as compared with fine list. What may be the reason for this? What may be the reason for this?
Because like the blocking thing, like
yeah, no, not because here we need to equate the lock on many number of nodes, right? In the course list, even the contention on the head, we need to equate the lock on only head node, right?
yes,
once a thread equates the lock on the head node, the remaining yes, that particular thread can comfortably perform the required operation. Suppose see, here we are trying to increase the number of threads. When we're trying to increase the number of threads, yes, for 2 threads, do we get any better performance? We are going to check it. Yes, definitely we observed a little bit more performance. Actually, in the earlier case, we observed the less throughput. Here we observe the better throughput, right? As compared with single thread execution. Okay. Instead of 2 threads, we are going to consider 4 threads. Do we get any better throughput? (0.2). Suppose here when we consider, here it is 0.1, here it is 0.15, here it is 0.2. That means actually this implementation is scalable. That means suppose if we have a sufficient number of resources, we can get the better throughput. Do you get my point? Suppose here this is a laptop with 8 cores. Suppose if you run this particular program on the server with 64 cores, you can observe the better throughput if you supply the more number of cores, right? Do you get my point?
Yes, sir.
Yes. Okay. Actually, from these two implementation, here we can say that a list implementation without logs gives the better performance because coarse-grained gives the better throughput as compared with this fine list implementation, right? Fine-grained implementation, right? When the number of threads is 1, it is 0.54. Here, when we consider number of threads is 4, it is 0.2, right? So definitely, what is the point of writing concurrent programs? There is no point. But then, yes, suppose we are going to consider one more synchronization, that is optimistic synchronization. Here we are going to look at optimistic synchronization.
Sir, one doubt.
Yeah, please go ahead.
Sir, at 8 number, like at 8 threads, the throughput decreased. Like, exactly why?
No. Actually, this throughput, usually while calculating throughput, we need to consider average of 5 runs or average of 7 runs. Yes, average of 10 runs. Reason is that actually, usually in the concurrent execution, there may be some outliers. It depends upon some other one. That is one thing. Second one is, actually, when you look at my laptop, LS CPU, what you can find? You can find that cores per socket is 4. Cores per socket is 4 and threads per core is 2. Okay. I have actually 4 physical cores. I have actually 4 physical cores. Okay. And each physical core can be counted as a 2 logical core. That is why total number of cores is 8. That means these 2 physical logical cores shares the same ALU. Same ALU in the physical core. Are you able to understand point?
Yes, sir.
Yeah, in that context, what will happen? These 2 cores, okay, that means these 2 threads putting a request to the same hardware unit. If those 2 threads put a request to the same hardware unit would not allow more than 1 thread at a time. Suppose if some other thread put a request to the some other hardware unit, then we'll get the better performance. If both the threads put the request to the same hardware unit, okay, definitely it won't allow both the threads, right? Did you
Yes,
get my
yes.
point?
So more contention than
So, some more contention. Actually, there also we need to maintain out of order execution, right? Okay, because of that, we'll get a problem. Next, one more reason may be there. Here, if all the threads are going to update same cache block. Okay, yesterday, Dr. Saurabh discussed about fault sharing, right?
Yes, sir.
Yeah, when actually, if a particular thread works on a particular cache block, if some other thread updates that particular cache block, then what will happen? That particular cache block is going to be invalidated. Okay, then the first thread observes a cache miss. If first thread observes a cache miss, definitely it takes more time to perform the required operation. In that way, actually, in that context, also execution time is going to be increased. Okay.
Yes, sir.
There are many cases we have to study. Okay, to reason for that particular output, we have to dig into the some other internals. Then only we can do that. Okay. In that context, we are going to use MSR registers, right? Okay, and perf tool. By using perf tool, we can measure, we can identify the cache misses, cache references, and all those page faults and all those things. By using those MSR registers, we can study a little bit more.
Yes, sir. Got it.
Okay. Next one is optimistic list. When you look at this optimistic list implementation, this is also pretty much straightforward. What is the problem with this fine list implementation? What is the problem with this fine list implementation?
Like too much of contention because of locks, like at each point.
Yes, actually, in the search process, okay, actually, we are going to equate the lock on all its predecessors, right? Suppose if you need some node, right? Some node is the required node. Actually, when we consider this fine-grained implementation, we are going to equate the lock on all its predecessors, right? All its predecessors. That is a waste of time, right? Instead of that, scientists came up with different kind of synchronization technique. That is optimistic synchronization technique. Here, intention behind this optimistic synchronization technique is, okay, first of all, we are going to identify required set of nodes without acquiring any lock. Without acquiring any lock. Once we identified the, after identifying the required set of the nodes, we are going to acquire the lock on all those nodes. Once we acquire the lock on all the required set of nodes, okay, we are going to verify whether those nodes are reachable from the head node. If those nodes are reachable from the head node, then we can comfortably perform the operation. Otherwise, there is some wrong with our locking procedure. Okay, where it go wrong? Reason for that is actually once we identified, after that we are going to acquire the lock. Okay, there is some interval, identification and acquisition. During that particular interval, some other thread, okay, changes the data structure. If some other thread changes the data structure, okay, then this particular thread has to traverse right from the head, right from the beginning. That is the problem with optimistic synchronization. Usually, optimistic synchronization is worthwhile only if it succeeds more often. Only if it succeeds more often. Okay, that is why we call it as optimistic. Right. Here, when you look at this particular logic, okay, when you look at this particular logic, here constructor is just like fine list and coarse-grained list. Here there is another function that is validate. When you look at this particular function, it has two arguments. Okay, predecessor and current. Okay. Yes. Suppose predecessor and current are the required set of the nodes to perform a particular operation. So in the validate method, what are you going to do? Verify the nodes, predecessor and currents have not changed in the interval between when it was inspected and when it was locked. Do you get my point?
Yes, sir.
Okay. So in that context, for that, what are we going to do? We are going to use this particular logic. What is this logic? Okay, initially node equal to head. Okay, while node dot key less than or equal to predecessor dot key. Okay, right. If node equal to predecessor, that means that is the required one. That is the last step. If node equal to predecessor, then we are going to verify predecessor next equal to current. If predecessor next is not equal to current, there is a problem. If predecessor next equal to current, there is no problem. There is no change. No change in that particular interval. Okay. Did you get my point? Yes. Here we actually in that particular add method, when you look at this particular add method, here we are going to identify the required predecessor and current with the help of this particular set of statements, with the help of these 4 statements. After that, we are here in the line number 27, we are going to acquire the lock on predecessor and current. Once we acquire the lock on predecessor and current, we are going to validate it. We are going to validate it. That means whether predecessor next is current or not. If predecessor next is current, then we can comfortably execute these set of statements. If predecessor next is not equal to the current, then what will happen? When we look at this particular one, again, when we look at this particular one, this one is in infinite while loop, right? This one is an infinite while loop. Are you with me?
Yes.
Yeah, again, that infinite while loop is going to be executed again and again. That means again, we have to traverse right from the beginning. Predecessor equal to the start head. Again, we have to identify the predecessor and current. After that, again, we have to acquire the lock and so on. And so on. So this optimistic synchronization is worthwhile only if it succeeds more often. That is an important point here. Are you able to follow?
Yes, sir. So if there is, it doesn't like find that node at any point, then the while loop will continue going on. So it will.
No. We have to come out, right? How do we come out? I will explain that. Which one? Here, suppose we are unable to find it. Okay, what will happen? This condition is going to be satisfied. That means in the concurrent context, somehow or other, that particular relation, that particular field value is going to be changed. Do you mean that? What do you mean by that?
So like let's say in add, okay, yeah, right. So it's at some point it should be true.
At some point it should be true, right?
Yes, sir.
Yeah. Yes. Next one. Yeah, when we can execute this method in the same way. Next, I would like to execute this lazy list. When we look at this particular lazy list, okay, here based on the when we consider that particular PPT, we observe that one more field is added to that node, right? What is that? 0 or 1 added to that particular one, right? Did you get that? When you look at that particular PPT, okay, in lazy list, actually what are we doing? We are postponing the hard work. How are we postponing the hard work? By setting the flag bit. We are postponing the hard work by setting the flag bit, right? Are you with me? Yeah. Here, I would like to explain it by considering this particular one. When you look at this particular one, are you able to see the screen? Rishikesh?
Yes, sir.
Okay. When you look at this particular screen, here each node, for each node along with the data, we added one more bit field, right? That is either 0 or 1. Okay. 1 means actually that node is present in the list. 0 means that is logically deleted from the list, right? Okay. Initially, we are logically deleting the node. Later, we are going to physically deleting that node from the list. Okay. Here, what are we doing? Actually, in the lazy synchronization, we are postponing the hard work. That means usually this lazy operation will be used for the deletion operations. If we consider binary search tree, deletion of a binary search tree is somewhat costly, somewhat difficult as compared with insertion. Okay, binary search tree, suppose if you want to delete a node with 2 children. Okay, in that context, we have to delete that particular node. We are going to replace that one with its successor or its predecessor. Yes, there are some questions. Okay. Yes. Now, when we go back to this particular program, here you can see that this node has, along with the key and next field, one more is there, that is marked, whether that particular node is marked or not. If marked value is false, means that that particular node is in the list. If marked value is true, means that that node is deleted, logically deleted from the list. That is the meaning of that. Okay, after that, similarly, just like optimistic implementation or fine-grained implementation, we can acquire the lock at the node level. We can acquire the lock at the node level. Okay. Here, when you observe the difference between previous one and this one, here you can observe that contains operation is the lock-free operation. Without acquiring any lock, okay, we can perform the contains operation. That is the one difference between the previous one and this one. Next one. When you look at this particular validate method, okay, their validation is done right from the beginning, right? We are traversing from the head. Here we are simply validating with the help of these 2 nodes itself. Once we identify the predecessor and current, we are going to verify that if predecessor is not marked and current is not marked, later if these 2 are satisfied, then we are going to verify this particular one. Predecessor next equal to current. If all these conditions are satisfied, then it returns true. Otherwise, it returns false. Are you with me? Are you with me?
Yes, sir.
Yes. Here, when you look at this particular logic, here we are going to identify predecessor and current with the help of this simple while loop. Later, we are going to acquire the lock, predecessor lock. Okay. Later, we are going to validate the predecessor comma current. Validate the predecessor comma. Here, you can find one more difference. Difference is actually in this add method, we acquire the lock on only predecessor. In linked list, when we think carefully, for insertion, lock on predecessor is sufficient. For deletions, we need to acquire the lock on 2 nodes, predecessor and current. Why? Think about it. That is an interesting problem. You can think about it. Definitely, you will find a solution to that. Or if you have any problem, please let me know. I will explain it in detail. Next, here we are going to validate. Once we identify the predecessor and current, we are going to validate it with the help of this particular function validate. If it returns true, then we are going to verify if current.key equal to key. That means already present. If it already present, it returns false. Otherwise, we are going to create a new node with the required key. New node next equal to current, and predecessor next is node. That is LP of, this is the LP of add method. Returns true. Finally, it is going to unlock the predecessor. That why it unlocks only predecessor? Because here we acquired the lock on only one node. That is predecessor. While performing the remove operation, while performing this particular remove operation, here we acquire the lock on predecessor and current. Once we acquire the lock on predecessor and current, then only we are going to validate it. Okay. Later we are going to verify it. Whether current.key not equal to key. That means suppose to perform a delete operation, that node should be present in the data structure, right? Then only we can delete it. If current.key is not the required key, then it is unsuccessful case. Otherwise, it is successful case. In that successful case, here what are we doing? Here we are doing current.mark equal to true. That means we are logically removing that particular node. Once that particular node is logically removed, okay, then we are going to remove that node physically from the list. For that, we are going to use predecessor.next equal to current.next. Finally, we are going to return true. Okay, finally, we are going to release a lock from both the nodes, current and predecessor. Okay, anyhow, contains actually here we don't need any lock at all. think about why here why we did not use any log for developing the contains method. Now I'm going to execute this particular one. Lazy list. Okay. Java C. Listed star Java list test. One is the number of arguments, first number of threads, range of keys 2000. Amount of time is 10,000 milliseconds. Prefill is 50. Contains operation is 50. Insert is difference between 75 and 50 is 25. 25 is the insert operations. All remaining operations are delete. So 50, 25, 25. Yeah, prefill is done. Prefill is done. Okay. Let us see. Yes, here we observe that throughput is 0.51. It's very close to the coarse-grained when number of threads is 1. When the number of threads is 2, let us see. .6. So here we are getting the better throughput as compared with any other implementation. When number of threads is 4. When number of threads is 4. 1.07. I think, did you see the improvement? Hello?
Yes, sir.
Yeah. So when you look at this particular one, okay, here you can clearly observe that, okay, lazy list implementation is scalable as compared with any other implementation. When we consider concurrent linked list implementation, lazy concurrent list implementation is scalable as compared with any other concurrent implementations. Okay. Yes. Last one is log-free list implementation. Anyhow, I would like to share that particular code with you. Please go through that and execute that. Okay. Do you have any problem? Most probably on Saturday we have one more session on concurrent implementation of data structures. In that particular class, I would like to clarify your doubts. Yes. Do you have any problem? Any doubts? I'm here to. Yes.
Lazy list. Why do we first delete it logically and then delete it physically?
No, that is the problem. That's what I told to you, right? Here in lazy synchronization, actually physical deletion takes more time, right?
Yes, sir, but we anyhow do it, right?
Anyhow we do it. Okay. Then what are we doing? Actually, and that particular logical deletion, with that only we can write the log-free contains operation. Otherwise, it is not possible to write the log-free contains.
Okay, sir. So deferring it to the end.
No, suppose if you don't put that particular logical deletion, okay, definitely contains operation is a log-based operation. When we include that, then only we are able to writing the log-free contains operation. Otherwise, it is not possible. It is not at all possible.
Okay, sir. So that time for contains operation reduces.
Yeah, yes. That is the reason. That is why when you observe that all the remaining methods in this one, here we don't put any lock at all, right? Okay.
Yes.
Not only that, okay, when you look at the optimistic one and this one, in optimistic one, we are traversing right from the beginning. Okay. Here we need not traverse right from the beginning. We are going to verify that particular one with the help of those two nodes itself. When you look at the validate method of this optimistic synchronization and lazy list synchronization, in lazy list, we are not going to traverse right from the beginning. We are going to verify these two nodes. Based on that, we are going to decide it whether that particular required nodes in the list or not. Reason is that when a node is deleted, that particular flag value is set to true, right? Suppose if that particular flag is not at all there, right? How do we know that whether that particular node is deleted or not?
Yeah, so like it might be in the process of getting deleted.
Yeah, again, we have to verify right from the beginning. Okay, that is waste of time. We can minimize that with the help of this simple logic, simple by using with the help of this simple extra bit field.
Okay, so it's about it.
What else? Oh, okay. Anyhow, I will share this video in that particular web page. Okay, NSM concurrent programming YouTube link. Okay, you can go through it, because to understand all these concepts, it takes time, right? Okay, that is why people are calling it as the concurrent programming is an art. It is not a science. So we have to think in different directions. At the same time, debugging of concurrent programs is much harder as compared with sequential implementation. Okay, this linked list is kind of very toy example, right? Okay, suppose if we try to implement BST or red black tree, then sometimes we end up with deadlocks, infinite loops. Sometimes it is very difficult to identify, okay, where is the error? Why are we getting this deadlock? It is unable to detect. It takes so much amount of time, right? There are no proper tools to debug that particular error. Okay.
Yes, I got it.
Okay. Thank you. Thanks a lot. Any other questions? Yes, sir. Improvement is significant. Thank you. Thanks a lot.